Hello everyone, my name is Saad, and today I'm going to be presenting my midterm report for Management Science class. My topic is the optimization of logistic costs using linear programming. And here is my content for the presentation. Now, as you all know, the logistics are the heart of any organization's business process. The main goal of logistics is to have the right amount of inputs at the right time, taking it to the appropriate location in good condition, delivering it to customers at the right time, and build and improve the supply chain to meet the increasing demand of customers. Which takes us to this problem because the logistics costs make up a significant portion of the total costs of enterprises, which drives companies continually to find ways for reducing logistic costs while still operating their business efficiently. While doing so, companies face the problem of lowering their transportation costs while satisfying the supply and demand limits. Therefore, it's very important to learn how to optimize logistic costs using linear programming model. The transportation problem is one of the subclasses of linear programming problem, where the objective is to transport quantity of products from different factories to different destinations in such a way that the total transportation cost is at its minimum. The objective function of this model is to minimize the cost of every unit shipped from warehouse I to destination J. Objected to two constraints. The supply constraint, when the total unit shipped from warehouse I to every customer J must be lower or equal to the warehouse supply, while the demand constraint, where the total unit shipped from every warehouse I to customer J must be greater or equal to the demand of destination J. Next, we're going to have an illustrative case for testing the model. In this case, I have two warehouses and three destinations. When dealing with a transportation problem, we first have to determine whether the problem is balanced transportation problem or unbalanced transportation problem, which can be determined by evaluating the total demand and supply. If the total demand and supply are the same, then the problem is balanced. But in this case, the problem is unbalanced. Now, since the demand is greater than supply, so we need to introduce a dummy variable. In this case, it will be a dummy warehouse. The supply from the dummy warehouse will be the difference between supply and demand, which is 240. And the cost of shipping from this warehouse will be 0. Represents our balanced version of the transportation problem, where the supply and demand are the same. So now we can proceed to find the initial feasible solution. In my reports, I used two methods for finding the initial feasible solution. The first method is the Northwest Carnem method, and the second one is the Vogel's approximation method. For the Northwest Carnem method, we start by allocating the upper left area of the table, which in this case will allocate 400 units for destination 1 from warehouse 1, and the rest 140 units will allocate it from warehouse 2. Then we multiply each cost by the number of units allocated for the destination. The total cost using this method is $11,860. For the Vogel approximation method, the procedure starts by selecting the two lowest cost cells for each row. Subtracting the lowest cost from the other will produce a Vogel number. We select then the largest Vogel number and allocate for the corresponding lowest row, which in our case is the second row. We will allocate 540 for the first destination from warehouse 2. The total cost of transportation using this method is $16,140. Usually when we are solving the transportation problem, the initial basic feasible solution cannot be considered as the optimal solutions because there might be better solutions. Therefore, we need to make the optimality test to improve our solutions. I use the stepping stones method to check the optimality of my solution. The stepping stone method evaluates the unallocated cells and reallocates the cells with the highest opportunity cost. The highest opportunity cost in this case is -2 and it's for the third row and first column. That will be our entry points, and we will make a loop by adding 140 for dummy warehouse 3 to destination 1 and subtracting 140 for warehouse 2 to destination 1, and then we will add another 140 to destination 3 from warehouse 2 and subtract 140 to destination 3 from warehouse 3. The total cost using this method is $11,580. And then we use the same optimality test for checking the optimality of the Vogel approximation method. And the total cost using this method is $15,620. In conclusion, both these methods gave different results for the initial feasible solution. The northeast corner method gave $11,860, while the Vogel approximation gave $16,140. This analysis shows that the northwestern corner method was the most efficient because it has the lowest cost after the optimality test, which is the same as before the optimality test, $11,860.